So good afternoon, students. We are here for this discussion on the safety of advanced nuclear reactors, and the speaker for this morning will be Dr. Nitendra Singh, basically a nuclear engineer, and presently he is working with the Institute of Radio Protection and Nuclear Safety in Cadarache, France, as a visiting research scientist. Before that, he did his PhD at Bhabha Atomic Research Center, where his thesis was focused on the core catcher design for advanced nuclear reactors. So I think he'll be the best person to talk about advanced nuclear reactor safety aspects. And he has been an ORFI research intern at the ORFI Research Reactor at CEA Saclay during his MTech. Before that, he has also worked for some time as a research intern at Indira Gandhi Center for Atomic Research. So, without taking much of the time, I'll hand over the forum to the speaker. Thank you so much, Nitendra, for joining. And I thank all the participants for joining on Sunday afternoon, sparing your free time and joining for this interaction. Thank you, Nitendra. The stage is all yours.
Thank you, Archana, for the kind introduction. And yes, I agree to you. Sparing time on the vacation is really, it shows the interest students on the topic. So yeah, feel free to ask anything during the conversation. As I mentioned, it should be more of an interactive session. You need not to just listen to me, because I'll not be covering all the data or something which you need to mug up or stuff, but we'll be focusing more on understanding. So yeah, today I'm going to discuss more about safety, basically nuclear safety in advanced nuclear reactors. So let's begin. So very first of all, when we say nuclear safety, what do you basically understand by nuclear safety? So there is a proper definition which is defined in International Atomic Energy IAEA tech docs, and it was defined very well. After a long time, they have improved it. So far, everyone across the globe is uh, basically taking this as the standard definition of nuclear safety, which states the achievement of proper operating conditions, prevention of accidents, or mitigation of accident consequences, resulting in protection of workers, the public, and the environment from undue radiation hazard. So if you try to understand this is basically a brief of everything we want to say about nuclear safety, which states like our primary objective is to protect our workers, our public, and the environment from any kind of radiation hazard. So if you read it from back to first, then you will understand that this is the primary goal or primary objective all the nuclear industry people, personnels, designers, operators, everyone associated with this industry has to follow. So likewise, how you from where these radiations hazard are coming, they might be coming from accidents or some deviation from normal operating conditions, and likewise. So if you want to prevent that, you need to maintain a proper operating condition, or you must say like the safe or the standard operating conditions. So this way, and so I assume when I'm discussing this topic with you, all of you are well aware about the basic design of nuclear reactor. You understand what are the main components of a nuclear reactor. You have fuel, clad, and all these internal components of a reactor combined well within the containment. This is what I'm assuming.
Yes.
So yes.
They are fifth semester plus students, so almost all of them are aware of the basic design.
Yeah, that will be nice. This is what I'm assuming that you all. So this is the basically a definition of nuclear safety to begin with. But my question is, why we actually need nuclear safety? What is so important about it? What do you understand, like why it is necessary? So I would say, as in the definition it was mentioned, from the protection of personnels from radiation hazard. So now the concern is, are radiations only concerned or there are other aspects as well? So this we need to understand, like when we say we need to make our nuclear plants safer, or when we talk about nuclear safety, so first thing which we need to understand, like why it is important. So radiation hazard, yes, of course. From where these radiations are coming? They might be coming from your fuel, but the fuel is very well within the core. They might be coming from other accidents, but why these accidents have happened? And as we are saying as a designer, or we are saying that if we want to have a safe reactor, then why we really need to have this nuclear safety aspect? So coming to the next topic, why we need it. So as I mentioned, if you want to protect your environment, your people, you need to maintain this radioactivity well within the boundaries. So to do so, there are three mainly safety functions. When we say, we basically say three C's in general. So like control of the reactor power, cooling of the fuel, and confinement of the radioactive material. So let's discuss one by one. So control of the nuclear powers. So you all know that nuclear fuel is a very dense source of energy. So it has a lot of energy to give you. So if you need to control it in such a manner that you can utilize it for the generation of electricity. Otherwise, it has a lot of energy. So you need to control that in order to in order to generate the standard electricity production. So you need to control the reactor power in such a manner that it should not exceed from your safety limits. So how you do it, that we'll discuss. So you need to, like if you understand the basic physics, there is a uranium as a fuel, for example, you bombard it with the neutron, and if you have a lot of uranium atom or nuclei, then if you keep on bombarding with neutrons, there is a chain reaction which is uncontrolled because of presence of so many uranium nuclei, and in each nuclear reaction you are having additional neutron generation, which can give you additional chain reaction, or an uncontrolled chain reaction. So you need to control that power, you need to control that reaction to have the better operating or better functioning of the nuclear reactor. So this is one. Secondly, cooling of the fuel. Why fuel need to be cool? So one, in on normal condition, you say because we need to cool the fuel because we want to take out this energy. We want to convert that energy into using that energy. You want to convert the coolant into the steam, and you want to generate the electricity. That is one aspect. However, there is another aspect which is like, even if the fuel is not, or the reactor is shut down, for example, so the fuel is still releasing some energy which is called as decay heat, which comes mainly from the fission products. So when you have like nuclear reaction between you with uranium and neutron, you generate some fission fragments which they continue to decay, and they keep on generating some decay heat, as we call say, and which is quite enormous. For example, if you are having a 1000 megawatt electric of 1000 megawatt of a reactor, then even if this decay heat is point, I mean 1%, then it's huge. It's like it's like 10 megawatt you are having out of nowhere, which is a huge amount of electricity, or a huge amount of energy, so to say. So you still need to cool that fuel. So somehow, even if you don't cool it, then what will happen? So yeah, one thing I want to mention in the first topic as well, if you don't control the reactor power, what will happen? It will exceed the reactor power. It will produce enormous amount of energy which you will not be able to handle, or which you will not be able to manage. So if you don't cool the fuel, it will keep on generating energy, and which will result in increase in the temperature of fuel. you understand. If the fuel temperature will increase, then the surrounding clad temperature will increase. With the increase in this surrounding clad temperature, there is a possibility of failure of this clad, which will result in the failure of other surrounding components, and likewise this thing will keep on happening. So you need to control reactor power. Why? To control the reaction and control the energy which could be generated. You need to cool the fuel so that the fuel temperature and everything should not reach should not raise to the level where the failure of the surrounding components and the structure is a concern. And third very important aspect is to confinement of the radioactive material. So if any of the two aspect, if you see the first and second, there is a possibility of radioactive release in the nuclear reactor or within the nuclear reactor. So if you go back to the definition, you understand we need to protect our environment or the people from this radioactivity. So somehow you need to maintain it within the system or within the zone, I would use the word here, uh, or to be precise, within the containment, because you should not, no radioactive material should go outside the reactor. Then only we can say we are able to maintain a reactor safe, or radio nuclear safety is maintained. So these are the three safety functions around which your entire nuclear industry is focused. Everything you do is mainly to maintain these three functions in a nuclear reactor. One more concept, how you maintain these safety functions. So the concept you basically maintain this safety function is using the defense in depth philosophy. So what is this defense in depth philosophy? I'm sure all of you are aware of this Matryoshka, which is like in a common day known as the Russian dolls. They are the doll within dolls within dolls, you know. Likewise, so you have a small doll which is encapsulated in another doll, which is encapsulated in another doll, in another, likewise. So you have a layer of dolls. In a similar fashion, we have this concept of defensive depth, which is a key factor for the safety of nuclear power plant. So the concept of defense in depth is not only for nuclear power plant, it is applicable in any condition. It is very well applicable and is being used as well in aircraft industries, I mean in aviation, in your IT industry for all the firewalls and all, and of course in nuclear industry, but in many another industries where the risk factor is high, you know. So we apply in a nuclear industry, we apply the concept of defense in depth since inception of the design, and we begin it during the construction of the power plant, and we apply all the principles to develop this concept and culture within the design as well as in operation. And this is continuously developed or improved based on the international operating experiences, because uh, not all countries can basically have all the experience. We have different type of reactors working across the globe, like for the moment around 438 different type of nuclear reactors are operating across the globe. So they all have a different kind of experience, different type of experience, and different timeline of the experiences. So they all work together to improve this concept. Now the thing is, what is defense in depth? We mentioned like it's something layered, and you might have seen this picture for quite a long time. This is something you'll find in all the text, all the IAEA document, every book. They say this is the different kind of layers you will find and different kind of systems you will find. So let's discuss a bit about it. I'm more fascinated with the other pictures which I'll show you later. But just briefly, so what this basically says, you have safety barriers. So the first barrier is the your fuel itself. because the fuel is so designed that all the fission fragments and everything are within that, remains within that fuel itself, which which is encapsulated within a fuel clad or a fuel rod or a fuel pin, different type of names it has. It is the second barrier. Then you have the third barrier, which is the your primary circulation system, primary coolant system, or you can say. Then you have a um, fourth barrier, which is your containment or containment building. You have seen the dome around this thing. So likewise, you in some cases you also apply a fifth barrier where you have this exclusion zone. It depends. It varies um, depending on the policies of the country. And along with that, you also have the associated safety levels where you maintain, like, firstly, level 1, you try to prevent all the deviations from the normal operation. And level 2, you control, if something deviated, you try to control it. And in third, if something is happening, okay, you try to control the accident scenario within the design basis functions. So design basis scenarios are those where you have already thought that this might go wrong, and if this will go wrong, we need to provide this as the safety function. So these are design basis levels. And fourth level is, okay, now things are happening, you need to manage this accident, you need to control this accident progression so the damage could be minimized. And the fifth level, okay, if it is going outside the boundary, you need to be prepared for all the emergency responses for the public. So, like, this is the main idea. And how do you do it? You have different type of systems for each level and something like this. I'll come to that. I am more happy with this type of diagram, more colorful and more easy. So, like, as I mentioned, you have inherent properties of core, fuel, moderator, and coolant, which make it more safer. And you have a core inventory and different type of barriers, which I mentioned, like, fuel barrier, coolant boundary, containment barrier. Then, of course, the exclusion zone if you have something. And to maintain that, you apply some engineered safety systems, or sometimes we call it safety systems for the reactors. And along with that, you also have safety barriers which are already in place, which are like this which are mentioned. And along with that, in the advanced reactor, we say passive engineered safety features or passive safety systems that we'll discuss. So they all together now make your defense in depth philosophy for the nuclear safety in nuclear reactors. You might have seen this picture as well. I'm not very sure if you have not seen it. So as I was mentioning, so there are possibility, if you want to maintain this 5 level, how you can do it. So this is one diagram which I always wanted to show everyone. Like, there are design margins, and you can maintain every function within your operating limits. And how you can do it? You have to maintain quality in everything, quality in material, quality in people, quality in working, everything that you need to maintain that quality. Then if some deviations are happening, some deviations are there, then you try to control that using, for example, here they have mentioned, like, if there is a loss of flow, or it seems like water will be low to cool the fuel, then you try to make up with the water. And then in the next is safety. Okay, if something is happening, it's you shut down everything. Then, even then, in the shutdown situation, you maintain the shutdown cooling because of the decay heat. So you maintain the safety still. And if something is happening, you are not able to control, as I was mentioning, so you try to minimize the accident progression, so which is called as accident management. And if everything has happened now, the radioactivity is going out, then you try to work on emergency responses. So different way of explaining many things. And this is the more standard way, more textbook way. So there are the 5 levels of defense in depth, and these are the primary objectives which we need to follow for each level. And how do you follow it? This is the important part which we should discuss, as I was discussing in the previous uh, picture. So if you want to prevent all the abnormal operation or the deviations, you try to maintain the conservative design. As I was mentioning, you maintain the quality in design, construction, and in operation. Similarly, if something has happened, some deviations are there, then you try to control these operations and detect the failures. And for that, you use different kind of control system, limiting system, protection system, and other surveillance features. And if something is happening now, the accident is in progression, then you control the accident within the design basis. And for that, you use engineered safety system, as I was mentioning, and also of course the accident procedures to maintain everything within the design basis. But if something is beyond, if it is going beyond design basis accidents, then we call the term in it's the severe accidents. Then you try to control the severe plant conditions as much as possible. You try to prevent the accident progression. You try to mitigate the consequences of severe accident. You try to minimize the losses. And to do so, you use different complementary measures and accident management. And this is the very level 4. Earlier it was thought like level 4 is not the something which we will deal with, but after Fukushima, this is something which everyone has realized that we should work on this as well. Level 5 is the mitigation of radiological consequences. So after this, if radioactivity is releasing to the environment, then you try to mitigate that so that the you can reduce this significant release of the radioactive material, and that you do using your off-site emergency response. You may go for evacuation, or you may plan it in a different manner, and these days we call it as severe accident management guidelines, and or in some cases severe accident management strategy, where these two levels works hand in hand. And it's really important for all of us to understand as the designers or the operators that this is very important to manage, because this is directly associated with the people around. So coming to the technical part, so all philosophy done. Now, what are the advanced nuclear reactor? You might have noticed that I have already mentioned for advanced reactor, but how you will say what is an advanced nuclear reactor? So there is a brief definition which some designers decided. It's the nuclear power plant designs with a feature which required for the elimination of emergency planning in the public domain, for example. So as I was mentioning, the fifth level, the offsite emergency response or the emergency planning in case of severe accident progression. So advanced nuclear reactors are basically those designs which designers claim that they are so safe that you don't need to evacuate your people. You can make it within your city and things like that. So now the question is it really possible? On If you ask me, yes, it is very well, because as a designer you design all your things, and there are many new things designers added to the previously improved versions as well, and that's how you call them advanced reactors. So there are few key aspects which I don't know if it is visible to you. So they added like double containment system, they added the core catcher in the event of if the core is melting, and how to collect it, cool it, maintain it. They added the containment cooling as well, to maintain the integrity of containment. They added the separate safety systems for all different trains and different aspects, so that every to avoid the common cause failure and stuff. And they also added some sort of water pool, extra water pool, in case something has happened. So there should be some sort of water pool. So in different designs, this the placement of uh, different reactors, I mean different components may vary, but for the moment this is the brief about what could be the advanced nuclear reactors. So now coming to the safety characteristics of the advanced nuclear reactor. There are two main characteristics these advanced reactors have, which I want to highlight. One is inherent safety characteristics, and second one is passive safety systems. And these two all together take care of your plant in any situation. They try to give you all that confidence that your plant is safe in any scenario. So let's discuss about it. So inherent safety characteristic is the negative reactivity coefficient. I assume you all know about reactivity coefficients. So if in any case there is some situation where your fuel may try to have the different deviation, or your reactivity coefficient is trying to increase, in any case it is so maintained that even if you combine all the possible coefficients, even then the reactivity coefficient will not go in a positive side. Once it will not go to positive side, your reactor will always remain in the inherently uncritical situation. So you are always trying to make it in using the science or using the physics about it. You try to make your reactors of low power density, you know and you design it in such a manner that there is a very low excess of reactivity, so that even if you combined reactivity coming from the surrounding or from the structure material during the unforeseen situations, even then the reactivity or the power will not exceed the shutdown power, so that you can maintain that situation in a controlled manner using your safety systems. The third, which is very important, the proper material selection. This is where a lot of scope is there for research as well. I'll come to that. So proper material selection, what I mean with that, you try to have material which are having high specific heat, so that if the temperature or surrounding or the fuel is increasing, the structural integrity can be maintained for a longer duration. You should have high conductivity, so that even if you are having a little water or little coolant available in your reactor, it can still extract a lot of heat through the structures. So these sort of properties you try to select to have a better configuration. So these are the inherent safety characteristics which you apply in your advanced nuclear reactor based on the physics or a science, I would say. Then it comes the passive safety system, which is more of an engineering or the technology, I would say, which is of course based on the science. But when I say passive, by passive I mean that where the operator's intervention is not required or least required. So if you switch it on, or if you leave it just like that, it will keep on functioning on its own, and you are just like sit back and see, okay, everything is cool. So that's what is the passive safety system. And now you might be wondering how it is possible that you just sit back, there is no operator, and things are taking place. So I'll go to next slide and then come back here. This is one thing I think all of you might have read somewhere or seen in some phenomenology or in some in experimental introduction in your earlier classes, which we call as natural circulation. If you remember in our elementary classes, when you used to study, like if you increase the temperature of a fluid, of for example, if you increase the temperature of water, then its density decreases, it becomes lighter and it keep on rising high. So if you make one loop like this, for example, a closed loop like this, and at one point you heat it, You can heat it here, 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 wherever you want. If you heat it, then the density of this water will decrease. And since it's a closed loop, you have a limited amount of space and limited and the fixed amount of water. So it will try to expand, try to move up because it's lighter, and this being heavy, it will try to come down. And this gives a driving head, or as we say, driving pressure, or delta P driving, which basically helps in this kind of motion, a circular motion, which we call as natural circulation. So if you keep on heating this, so the temperature of entire fluid will keep on increasing. Then after a while, this head will try to keep minimize yourself, because your delta T, your delta temperature is now reducing. So if you want to maintain that, you cool it at one point. You can use any heat sink, or for example, steam generator or anything. So if you can maintain this kind of situation, that you heat it from one point and you heat it from a different point which is at a height, then you can maintain this driving force. Then using the science, you don't have to do anything. This will keep on, circulating there on its own. It will take heat, it will remove heat somewhere else. So this is basically the phenomena which is the basis of all passive systems. So coming back to this, so you can have like several kind of safety systems, passive, in advanced reactor, which are now being incorporated in many of the designs. So there, one is a very important is shutdown system. So once you shut down shut down a nuclear reactor, you, as I mentioned, there is a decay heat. So even if it is shut down, you have to cool the several components of a nuclear reactor. You can do that using the passive shutdown system. You can have a dedicated passive decay heat removal system, which is directly connected to your core and to your sink, like using the steam generator or outside sink, through which you can cool the core directly. This can be a one stage or two stage possibility. For example, you have the decay heat system directly connected through steam generator through this same loop, and then you have the steam generator which is cooled via air using the same loop. So in first kind, the core will be your heating end, and steam generator will be your cooling point. On the second loop, the steam generator will be the heating point and air will be the cooling point. So you can have a different type of coolant to maintain this sort of systems. So likewise, you can have a passive emergency cooling system. You can have like ECCS, when when there is a loss of flow, then you need to add some water directly to the core. So you can have this passively. Earlier, you need to have, operator should be attentive. If something is happening, he need to switch it on. But you can have this sort of response passively. It is possible that you put some sort of passive valves which detect the situation, which detects the level of water which is going down, and then accordingly actuate the emergency core cooling system automatically. You have passive containment cooling system. So you might wonder that why we need containment cooling. This is very important. I'll tell you why. So you can have a containment cooling. You have this containment, and then you can have the air cooler, or I mean the air natural circulation, which can take the heat from inside the containment and cool it using the air side, which is like always cooler compared to within in certain scenarios. So why containment cooling is important, you need to understand it. Containment is made up of concrete, and concrete has a lot of water, more than 50%, 60% is the water content in a concrete. So if your temperature within the containment is rising beyond 100 degrees Celsius, for example, then the water within this concrete will try to evaporate, or it will try to reduce. reduction of this water within the containment, within the concrete, will reduce the strength of concrete. And if, for example, if you remove all the water, it will crumble because it will be nothing but the collection of stones only. So somehow you need to understand that your containment should also remain cool. So you can have this passive containment cooling as well. And as I was mentioning, core catcher is one of the key aspect or key design feature for all the advanced reactor. In fact, all three mentioned below are the one of the key features of all the advanced reactors. So core catcher is something where you collect all the molten core and you try and maintain it, try to cool it and maintain it within the containment so that no radioactivity can go out. And similarly, you try to have passive hydrogen management. This you need to understand from where this hydrogen came, just like that. So it comes from the structural material. I was mentioning, if you are not able to cool the fuel, its temperature will increase. When its temperature will increase, the temperature of the clad, which is usually in thermal reactors, it's zircaloy, or it has Zr, zirconium in it. So that material will also heat up and its temperature will increase. So once this temperature is beyond certain limit, for example 1200 degrees Celsius, which is the most cases, it at that temperature, when it interacts with the surrounding, it gives the hydrogen, it reduces to give the hydrogen, and that hydrogen gets collected within the containment. And it's risky. Why it's risky? Because the hydrogen is inflammable, highly inflammable, and it may catch fire in presence of oxygen. Of course, you have a lot of oxygen and steam is coming in such scenarios. So it could be very risky. In fact, if you don't know, I want to tell you, in Fukushima, the explosion which occurred in the containment on top, it was not a nuclear explosion, it was actually the hydrogen explosion which occurred because of the accumulation of the hydrogen. So hydrogen which blew off the whatever containment they have. They didn't have much, but whatever they had, it blew it off. So hydrogen management is really important in that sense. And also, we need to have filtered containment venting system. So this is very important in this case. For example, if you have a lot of radioactivity within the containment, and it will keep on pressurizing this containment, which will again add the stresses on the concrete. So you want to reduce that stress on the concrete so that your um, containment integrity can be maintained. But if you release all this radioactivity outside, then there is no meaning of you are not maintaining your safety. You are not respecting your last confinement safety function. So somehow you can do that by filtered containment venting, which is like you filter out the radioactivity material, but you release the pressure outside. You release the gases outside, but you maintain the radioactivity within the containment. So this is possible, and they are being used for all advanced nuclear reactors. So to give you some quick example of one of the safety systems, you can have like many, but I'll give you one quick example of core catcher with a nice animation. So this is one of the advanced nuclear reactor which India is making, or in constructing in a few years. It has been approved. So in this case, we design one core catcher which looks something like this, which has some structure, and you have some sacrificial material to it, and you pour the water from down. So this is your core, for example. And they have, as I was mentioning, in all the advanced reactor, they have made a provision of water pool somewhere. So in this reactor, the water pool is on the top. Why it is on the top? Just to make sure that everything can work passively, because if you have water on the top, then through gravity it will automatically will come down, as simple as that. So you have this core, and due to some reason, some sort of this accident is happening and some core is melting, it will breach the structural component of core. It melt is coming down, it interacts with sacrificial material, and then due to decay heat it forms the melt pool like this. Now everything is passive. There is a passive actuator valve which will detect it, and it will release the water supply, which will form the water from the bottom, and it will then passively go through the melt, and it will convert into the debris, which will then automatically be cooled. You can see here through the water pool, and this steam is can be collected within the containment or can be released through the filter containment system. And that's how you maintain this passive core catcher in a nuclear reactor. So this is one of the design which we did recently. And now you should question one thing. Okay, this is the scenario in a reactor, but how you basically design it? So to design it, like this is a concept you design, you need to validate those concepts, which you can do using the experiments. So how you recreate such scenarios in the experiment, I'll give you one example of this, which is like this. So instead of core, you use furnace to generate some simulated material or whatever material you feel like to study the properties, and then you transfer it into the test setup. So this test setup is here, which is like this. So this is a two-stage animation. Okay, so in one case you basically generate the melt, which is then poured through some funnel arrangement or something into the test section, and this test section is basically now your reactor scenario. So as I was mentioning there, the melt comes down, it interacts here, it makes the pool, and then you add some decay heat to it, then water releases into it, and then it forms the debris, it cools down, and you collect all the data, all the measurements you do, and you study. So you design this concept, you validate those concepts, and then you use these concepts directly into the reactors. This is how you do it. So concluding my presentation, what is most important for us is the nuclear safety, and nuclear safety is utmost priority for the nuclear industry. And as I was mentioning you, like innovations are the key. You need to come up with new ideas, new possibilities, new technology to make sure that you take care of different kind of situation. And uh, by a different kind of situation, I mean you need to be prepared for the worst case scenario. Whatever you can think beyond, you need to be ready for that beyond. So that's how you try to maintain the safety in all the advanced reactors. You have different kind of systems, different kind of technology, and they work all together, and somehow you try to minimize the human interaction or human intervention or the operator's intervention to it, so that even if in unforeseen scenario where operator is not available or operator is not able to reach, or something has happened that there is no access to the control room or something like this, even in that scenario your reactor will remain safe on its own. That is one of the main feature of any advanced reactor which will be coming in future, which are already under design and some are already under constructions, and a few of them are already operating now. So that's all from my side. Thank you so much, and if you have any question, I am ready to answer them. Thank you.
Thank you,
Thank you,
Nitendra. That
Nitendra.
was an
That was
excellent
an excellent
presentation. I think
I
Piyush
think
has one
Piyush.
question.
Yes, please.
Sorry for the echo. Piyush, you can unmute yourself and ask your question if that's possible. I can read out his question. He says that you were talking about a source. So, from what source do we bombard neutron in the nuclear fuel? And were you referring to all nuclear power plants?
Where
This
I
was
was.
during the initial part of the presentation where you were discussing about that neutron is to be bombarded, yeah, in the nuclear fuel section. So this question
Okay.
he asked beforehand. Yes,
Okay, okay, here. So yeah, of course,
yes,
I'm talking about all nuclear reactors. Basically, in you all know, in you have this nuclear energy because of you have a nuclear fuel and you bombard it with neutrons. Then only it initiates nuclear reaction and it continues the nuclear chain reaction, and you try to maintain that chain reaction. So yes, I am talking about that particular physics phenomenology which occurs in all nuclear reactors. If I may, if I am able to answer you, or if I have understood correctly.
yes. I think he'll
Are
write the
we taking
response.
any outside source of neutrons? Hello, am I audible?
Yes,
Yes, Piyush, please go ahead.
Nitendra, I think he is asking about any external source that we are keeping for neutron. Is that
Ah,
right,
okay.
Piyush?
Yes, ma'am.
Yes.
Yeah, so you were asking about a very primitive scenario. Okay. So once you start a nuclear reactor, for example, you have constructed a new reactor, you have put your new, very brand new fuel inside the core. Entire core is new, entire fuel is new. There is no source, only the fuel. So there is no neutron in the surrounding. So you need first neutron. If I would say, you need first neutron to start the first nuclear reaction, which will then generate the further neutrons. So yes, except for the Russian designs, in all nuclear reactors, you put one source below the core, which do or which performs two functions mainly. One, it gives you the initial data to the control room, which you know, okay, how many electrons, how many neutrons are there, what is the surrounding and everything. And then once this neutron source start or once you start removing the control rod for the first time, I'm talking about when you start removing the control rod very little, then it interact with the surrounding fuel, and then it gives you the first chain reaction or first couple of chain reactions. Then it increases the neutron flux. Then again, the surrounding keep capturing this increment of neutron flux likewise, and then you attain a different power. This is what we call as criticality of a reactor, or the reactor went critical, or you can say the reactor actually started. So yes, in the beginning, all the reactors except for Russian designs, you have the neutron source. In Russian design, they use different technique. For that, a lot of experience is needed. They play um, with the control rods. So they play with the control rods and then somehow do it. So it's a different technology, I would say. But except that, all reactors have this initial neutron source. Later on, they don't need it because you never remove your all fuel out of your reactor. So there's always some neutrons are there. Even if you shut it down, there is a certain level where neutrons are still there, decay heat is still there, and then you can continue. Even if you refuel it, when you refuel, you don't refuel your entire core out, entire core in. You remove one third of the core, so the rest of the core is still having new neutrons. So somehow it is maintained. But yes, in the beginning, you need that source. Now I have understood, and I think I'm able to answer it.
No, but now I am in a state of doubt. How do they
Yeah.
do it in the Russian reactors?
Yeah, that's a cute thing. That's a cute thing. It's a new technology, they always say, but in Russian designs they do that. They don't disclose it, but
Okay, they
they
don't
do it.
disclose it. Okay.
Yeah, they don't do it, but they play it with the control rods. Because one more thing is they also use two different kind of control rods. Earlier, most of the reactor were using only one kind of control rods, but now all the advanced reactors they use many types of control rods. So using that, they could play.
Samir
So
says spontaneous fission.
yes, this is the one region which adds to spontaneous fission. They maintain it, but as I was mentioning, you don't do it because you need a lot of experiences for that. So no other want, because if there is some deviation, and then you don't want to uh, put yourself in that situation. So so only Russians do it, to be very frank, but
Okay.
nobody else in the world do it.
Okay.
Everyone uses the neutron source, and
Neutron.
I like that neutron source concept, because as I was mentioning, you have this to make sure your all data acquisition or your surveillance system is working fine. You have the initial data of the source, which can tell you, okay, this is the minimum neutron flux we have through the source. If any deviation is coming because of the increment of control rods, then you can actually detect it.
Okay.
So that's how they do.
I think next Rita can ask her question.
Okay. Thank you, sir, for the wonderful presentation, first of all. Sir, my questions, like I have two questions, and both of them are mainly from the licensing part of the nuclear facility. So
Mm.
the first one is like, how do what are the differences in the licensing of a nuclear facility in a country like India and the other countries which are the superpowers like US, France, China, and others? And my second question is that the licensing of a nuclear facility, like the generation two reactors and the between the generation 3 and 3 plus reactors, like just you mentioned that there are some safety aspects in the generation, like generation 3 and the advanced reactors. So what are the differences between them also?
Yeah. So coming to your first question first. So when you say some superpowers, in terms of nuclear technology, I count India as one of them.
Okay.
Because you might not know, but Indian nuclear technologies are one of the best in the world. Mark my words. So yes, I cannot differentiate in that sense, but yes, there are certain difference in regulations, and of course there are differences in licensing processes. It depends. It varies from country to country. Like you cannot say like US and France has the same, or France or Canadians have the same. They all have different aspects, but few key aspects are still the same. For example, everyone have the process of licensing in a very structured manner. You initially give the concept for the review. They review the concept, then you give the preliminary design, then they review the preliminary design, then you give a detailed design report with all your data, then they review your detailed data with their independent bodies, independent research, and they counter it. And then if everything goes well, then nowadays they also review your severe accident management planning. And once they are happy with that, then they ask you for the entire detailed report for the for all the processes. And this include your site selection, this include your design of the reactor, this include your operation strategy, your accidental mitigation procedures, your emergency preparedness procedures, everything. So they review it in on that manner everywhere, because somehow this is the standard which came out from the experiences globally. However, few things vary. For example, if I point out, if I take one example like PSA, probabilistic safety analysis, you do. So in US, they follow like event approach, where you define one particular event and you use your concept. Okay, if this event happened, then you use this procedure, and there is a defined criteria for that event. Okay, this for example, this neutron flux is this, water level is this, temperature is this, then you switch to a normal condition to this event. Okay, so this is like event approach mostly United States follow. However, in case of France, for example, they don't follow this. They go with state approach, like what is the state of the plant. So in for example, in the same scenario, they will not see what is the fixed temperature. Okay, you have to switch. You monitor the plant. Okay, you monitor what are the deviations. Is the temperature is really increasing beyond certain limit and we cannot control it, or the reactivity or the neutral flux is really increasing on certain thing, and you then evaluate, okay, it might go to this event, it might not go to. Once they are confident enough, okay, now it might go to this event, then they switch to the that procedure or the accidental procedure. So it this sort of minute things keep on varying with different regulatory board to different regulatory boards. Okay, so likewise in India as well, we have our own regulatory bodies. We also follow our own norms, our own system, and in India you have more strict rules compared to other nuclear industries. This I should mention. So somehow every country has their own way of doing and analyzing this sort of thing. Second part of your question, which says how the licensing process has varied when you talk about the second generation plants, third generation, and the advanced reactor or fourth generation, 4 plus. So of course, system varied because, for example, earlier you were not having passive system, for example. So now if you want to license where your design include a passive system, then regulator need to understand that system first. Then regulator need to test that system first. So they may ask you with the data, okay, give me your data, experimental validation, experimental data, which I will also get verified with my own experimental setup or the codes or whatever resources I have. Then once I'm convinced, I will allow you to do so. So with all these new things coming, the regulator also have to upgrade itself. So this is one change which few nations have done and few nations are still in the process. And secondly, like as I mentioned, one of the key component is core catcher. Not all nations are coming with the concept of core catcher first. Secondly, the core catcher is itself is a complex concept. So few people are coming with a different concept, few people are coming with a different concept. So then regulator has to understand what is good, what is bad, or what is good up to what extent and what is bad after which extent. So regulator also have to improve themselves very much. Third point, some earlier there were the thing like people were constructing reactors in their own country. Now one country is constructing in another. For example, in China, most of the people are constructing. In Egypt, people from China or Japan, they are constructing, or Korea is constructing, for example. In India, you have Russians who are constructing, and France is also constructing. So, when you design a reactor, you design it in with your own regulatory guidelines. But when you are putting it into another country, you have to follow their regulatory guidelines as well. So this also adds up a pressure on the regulator to upgrade themselves, to understand, or to be in sync with all global regulatory bodies. So this is one more change which you have seen, and the most recent I would say is the SMRs, the small modular reactors, which have come up. So there have been, for the moment there are like almost, if I remember correctly, 80 something plus designs across the globe on SMRs, small modular reactors in different countries. So, but so far only USNRC, which is the US regulatory board, they only have given the approval to new scale SMR. New scale is the company which made SMR, a small modular reactor in US. So now, and for example, in India, we still don't have any regulation about SMRs. So somehow, and not many country has, only US and RC has so far. Other regulatory boards are still working on it. So that's how you, because of the change in technology, because of the improvement in the technology, you basically upgrade or improve yourself as well as a regulator. So that's the change you will see in both your questions.
Okay, sir.
So
Thank
Nitendra,
you.
if I remember one of the slides, sorry
Yeah.
Rita, if anything was left,
No, ma'am. Thank you.
you mentioned in one of the slides that there is elimination of emergency planning. And as I understand, licensing requires an important consideration of even the emergency planning. That's also covered. So if this part is somehow taken care by the design and the inherent safety features, I think the licensing will become much more easier.
Yeah, so that's where the clash between a designer and the regulator comes. So, for example, I go back to 2010, for example, when they designed EPR. So EPR was one of the most advanced design at that time, and they were claiming it like, this is a reactor which can be constructed in the middle of the city without any exclusion zone, without any emergency planning. And of course, they included a lot of great safety systems, I would say. At that time, they were adding a core catcher. At that time, they were having so many passive system and stuff, but the regulators were not ready at that time. There were a lot of debate going on. uh, Designers wanted to do so not because they wanted to compromise with the safety, but they wanted to do it for gaining the confidence, like we can make such a safe reactor. Unfortunately, in 2011 March 11, of course, to be precise, Fukushima happened. And so those regulators who were like trying to think of, okay, let's give it a try, they again went back. No, we cannot think of, even if your reactor is that safe, it's okay, there's no harm in having an exclusion zone or the emergency preparedness, which is a wise thing, I would say. As you know, in nuclear industry, we always follow to have a redundant systems and the diverse system. So having one more redundancy, there's no harm in it. So as a regulator, if I am thinking, then I am thinking in a correct manner. This is one. Uh, Secondly, when designer wanted to say that we don't want to have any emergency planning, they were okay with it, but they were missing one aspect which I would like to highlight here. EPR, when they were proposing, EPR is like 1300 megawatt electric capacity reactor, which means like almost 4000 megawatt thermal energy you want to put in the middle of the city. So in any case, if any kind of deviation will take place, it's an added risk. Then why to add it? However, if you see the concept of SMRs now if you compare these two, because these two are the main designs, or generation 4 plus, if you compared with the SMRs. So generation 4 plus and SMRs both claim that we can remove the emergency planning in a way. So in SMRs, if you say the SMRs, the most of the designs are of 80 megawatt or 100 megawatt of this power level, which is okay, and also they are integrated modules type. The the chances of leakage are minimal because you don't have anything coming out of the pressure vessel, first of all. And in most of the scenarios, these entire reactor within the pressure vessel is already dipped inside a water. So the chances of core melt and stuff, they are eliminating that in a way. So of course, they are also coming up with this kind of claim. So it's okay in terms of a designer's perspective, in terms of engineered safety system. But in terms of regulation, uh, regulator is someone who is responsible for the public. They have to make sure that whatever is going to the public domain, it should be perfect. So if they are asking to have one more added level of emergency planning or exclusion zone, then there's no harm, I don't think. Of course, there is a added price to it, for the operator or for the designer or whosoever is constructing that. But in any case, our first priority is the public safety. So there's no harm in editing.
Yes, agreed.
That's what I feel.
Hmm. Okay, so next I think Shrish would like to ask a question. Shrish, please unmute yourself.
Yes, ma'am. Thank you, sir, for that presentation. Uh, in the beginning, you had started with the concept about safety, and you had also mentioned the IAEA definition and all of that. So my question is that assuming that TMI and Chernobyl had not happened, what would have been the state of the security measures that are taken by nuclear power plants in today's context?
So you have, if I want to understood correctly, you have mentioned security. You want to understand about security or safety, because they are two different things which work hand in hand.
Yes,
I
ma'am.
may comment on both.
Sir, it would be better if you could mention about both the
Yeah,
things.
yeah. So let's discuss the safety first, and then I'll come to security. So yeah, let me tell you in this manner. If TMI or Chernobyl would not have happened, so you mean to say if they would have happened, we might not work or we might not improve our safety level what we are having now. If I understood correctly, that is your concern. But
Yes,
let me tell you one thing. Before TMI and before Chernobyl was in April 1986, and TMI was in, if I remember correctly, May 1979. But in 1974, there was a report which was, generated by a team which was headed by Rasmussen. We call it as Rasmussen report or WASH 1400 report. It's a very famous document, very relevant for all the nuclear safety aspect. So that report, for the first time mentioned critical things about, like, they mentioned the possibility of core meltdown for the first time. They mentioned the possibility of, this common cause failures, and they mentioned the possibility of integrated failures, which actually took place in Fukushima, for example.
yeah,
So I'm talking about in 1974. So when they come up with the idea, designers at that time, they said, okay, it's a great report. It gives a great possibility to understand, and it's nice. Everyone appreciated, but designers were questioning, because in a way it was it was like you are questioning the capability of your engineered safety system, and indirectly you are questioning the designers, like what you have made. But it was not like this. So there was this debate started, you know like, we made safe, they report want more safe, this thing started. If I understand correctly, okay, at that time, we are talking about 50 years back, might have took a while to improve to this level. If I want to add one more point of it, as I am saying, like, after Fukushima, everyone wanted to have a passive systems. However, I recently mentioned, however, EPR already had that in 2010 when they were proposing to construct a reactor. They already have a passive system into their designs. So it is not necessary that even these things would not have happened. We didn't have this level of safety aspect now. This is one and very clear. What these experiment did, they reduced this timeline, so to say. Because once TMI happened, they saw the core melt taking place, you know, and then they understood, okay, even when and TMI was in US, okay, you cannot, US used to claim like we are the best in nuclear technology, and they saw a meltdown taking place in their own reactor. So everyone, and this report was also under USNRC, so they understood the criticality and the real vision of this report. So yes, these reactors in a way help the nuclear industry to consider all these scenarios which were hypothetical in the report, but now they are the reality in the life. So somehow they accelerated it further. And after that, if I say after 1979 only, everyone understood like all these analysis, all the report, or all these hypothetical situation with all the designers or all the um, like people, experts around the globe, they are thinking you should not ignore it in any manner. So this was the first lesson, and I would say one of the key lesson everyone in the nuclear industry took at that time, and it is still continuing. So all that core catcher research or this filter containment venting system I'm talking about, or this hydrogen management, this is under the research since then only. It has not started after Fukushima, so to say, or after Chernobyl, I would say. They started long back itself after the Rasmussen report. But of course, the phenomena are quite complicated, so research is still continuing, and we are still improving on it. So this is the scenario.
Thank you, sir.
Oh yeah, I forgot to mention on your security part as well. So yes, at that time security was not that much of concern, because the only concern when they were focusing on security was the war, because used to be a very prominent stuff at that time. So people were afraid if some war-like situation will occur, so you need to make sure that your nuclear facilities are safe.
Right.
And like in these and the superpowers at that time, they thought if you have uh, uh, you know the weapon of mass destruction, you are pretty safe, nobody will question you and things like that. The things went wrong in 90s when the terrorism started to rise, which increased the risk, and which in fact questioned the security aspect of nuclear facilities. So this was also the concern of the designers, to make sure, like for example, if you you drug the operator, for example, or if you kill the operator, so to say, in that hypothetical situation, then you will not have a operator available in your control room, even with your all safety systems, all everything is in that place, but still you don't have operator. So somehow, to consider this scenario and to address this scenario, people started working on passive systems long back. So I would say the passive system research experimentally started long back in 1970s or 1980s itself. And of course, with the improvement in technology, with improvement in data acquisition, with improvement in experimental possibilities, things got improved. And nowadays you are using artificial intelligence as well in the field of nuclear safety. So yes, everything kept on increasing likewise.
Thank you, sir.
If I can add to it, even the Indian advanced heavy water reactors had this passive safety system, and this was much before Fukushima. So they had
Yes.
developed everything before Fukushima actually happened. And post
Yeah, in
Fukushima,
fact,
of course, there were many changes that took place even in Indian reactors, and I think globally also major changes took place.
I would like to add to ASWR. You have mentioned advanced heavy water reactor. Yes, indeed, this reactor was designed in like 90s, and they have all the safety passive safety system. In fact, ASWR has this feature that it can even operate passively. It don't need any operator's intervention to even operate on its own. So yes, and this was like way back. If you read the papers on it, the complete design papers you will find in 2006, 2002, 2004 at that time. And Fukushima took place in it happened in 2011. So yes, Archana, you rightly mentioned. So people were working on this for long back. They wanted to have it more, but as I mentioned, the Fukushima alarmed everyone. Now you cannot ignore. Earlier, people were doing it by choice, but now it became the part of your the design or part of your thinking. So that's what will the major change, I would say.
I think both the regulators and the designers emphasize more on the safety features and actually are more sensitized towards these aspects. But it is like the others who are actually non-nuclears, it is their repulsion or hindrance which is increased after such accidents, which actually retards this entire motion. The nuclear industry is actually not taken or set aback by any of these accidents. So they
Indeed.
always gain. It is, I think, true for any industry that you gain from your accident. But of course, for chemical sector, we haven't seen such developments happening. For nuclear, they have learned a lot.
Yes, I want to add to it. You have rightly mentioned, like not other industry. Even if you take mining industry or you take a chemical industry, they have not improved a lot in this sense. Indeed, the two industry which I always respect and they go hand in hand because they are directly related to the people are the aviation and nuclear industry, and both of them you see the improvement. If you remember, there were a large increase in the aircraft accident in the late 90s because the people were more people were became more capable of taking those flights and flying. They had the economy started increasing, everyone wanted to fly, so number of flights, number of aircrafts increased at that time, and resulted in a lot many accidents taking place. But then they came up with new design. If you see the A380 or the Dreamliner, they came they were not just like that one day affair. Okay, we want to make an aircraft tomorrow, just do it. They had a long research for it, making such a big aircraft, you still keeping the dimensions of the wing and everything. They changed the entire aerodynamics, they changed the fuselage, everything. So this way you continually improve your research and to make things improve. This is one of the good aspect mainly taken care by two industries, nuclear industry and the aviation. So yes, things were people are walking, as you rightly mentioned, Ashana, like the designers or operator or all the people, or I would say all nuclear professionals, they were not at setback or they were not just sitting, okay, something will happen, then we'll start thinking. They were continually working to improve the safety and all the aspects. But these things just highlighted the concerns of the public. Yes.
Right. Any more questions?
Thank you, ma'am. Thank you, sir.
You're welcome, Shirish. Any more questions? Ikshita, you wanted to ask something? Or is it clear to you?
Ma'am, I wanted to ask, but then Rita asked the same question, and now I'm clear with it. Thank you so much.
Okay, right. So I think there was one question which Tushar wanted to ask. So Tushar is actually from the second year. He doesn't have much information about the reactors, and he wanted to ask about what actually happened in Chernobyl. And Samyak and Piyush together did a wonderful job in clarifying his doubt. So Tushar, if everything is fine, we can move ahead,
Yes,
or you
ma'am,
would
it's
like to
fine.
ask something?
No, ma'am, it's fine. Thank you, ma'am.
Right.
But one thing I would like to highlight here, which most of the people are not very much aware, they think like Chernobyl and Fukushima are the same. But I still want to highlight that Chernobyl and Fukushima are two very different accidents. Chernobyl was a kind of nuclear accident, I would say. However, Fukushima was not the nuclear accident. It was initiated by the natural calamities, but the accident which progressed was mainly due to the chemical reasons. The explosion was not the nuclear explosion; it was just the hydrogen explosion, which is a kind of industrial explosion, I would say, because hydrogen explosion can occur in several industries where you have a high temperature interaction and water interaction, maybe in a metallic industry and others. So yes, these people should understand that they are not the same accidents.
I think with no more questions, we can wind up this session. I thank you, Nitendra, for your time
My pleasure.
and this wonderful lecture. And I thank all the participants because it became interactive because you all were present. So I hope this session benefited you and you had some good takeaways. So I request you to just go to the Mentimeter and fill up the feedback of this lecture. In case you require something more, please let me know so that we can arrange for a further interaction. It has been almost like 1.5 hours since we started, so that's a long time. Thank you so much for to the speaker who has given us some valuable information, and to me also, because I just came to know that there are 438 types of nuclear reactors that are operating around the globe. So that's quite a different, quite a wide variety which is operating.
Not variety. 438 are operating of different kinds. Like out of which there are PWRs, there are VVERs and different kinds. But 438 are operating for the moment.
Total of reactors are operating. Okay,
Yeah.
right. Thank you so much. I hope all our participants could clarify their doubts. In case you have some more, you can let me know. I can pass on your questions to the speaker. And Nitendra, one more thing. Shirish wanted if you can to know that if you can share your presentation. So would that be possible?
Yeah. If you want, there's nothing in that presentation. I never. This is one thing. Okay, just out of this context, this I was discussing with one of my colleagues as well. I don't make this self-explanatory presentations. You can have it, but if you have any doubt with this presentation, you just write to me. I just try to put some figures to it and then try to make it more interactive. I'll send it to you, Archana. You can then share it.
Okay.
Yeah.
Thank you so much. So please, everybody, take care. See you again in some more wonderful interactions. Thank you, Nitendra. Take care. Bye bye.
My pleasure.
Good
Thank you, all
afternoon.
of you.